What I'm showing here is the velocity profile of air in two different cases. In the top case, the speed of the air far away from the flat surface is equal to 0.02 meters per second. So when I say that, I mean these velocity vectors here have a length of 0.02 far away from the flat surface. In the bottom case, u infinity is equal to 0.1 meter per second. So that we'd look down here, the length of these vectors is equal to 0.1. Note that we're using the standard notation in which the horizontal and the vertical components of velocity are given by lowercase u and lowercase v. A couple of things that we observe straight away is that v is about equal to 0. So the flow is basically horizontal in all cases. We also observe, by way of the no-slip boundary condition, is that u is equal to 0 meters per second at y equals 0, or at the surface, and u is equal to u infinity at large values of y, so where y goes to infinity. Well, let's define what we might call a boundary layer. And the boundary layer, we're going to say, is a location for any value of x, a location, a value of y, in which u is equal to 99% of u infinity. So in the bottom case, this would be where u is equal to 0.099 meters per second. So we know the velocity at the surface is 0, and it's not there, and the velocity far away from it is equal to u infinity. So I'm looking for a location in which it's about 99% of u infinity. So I would call it that middle dot right there. In the case where x, if we move to the right a little bit, the value u is probably 99% of u infinity at that location. As we move downstream, u infinity, u is probably 99% of u infinity there. Near the leading edge, the u might be equal to 99% u infinity there. And if I just crudely connect the dots as we come down, what we find is that the thickness of the boundary layer increases as we move down the length of the plate. We could do the same analysis for the case on the top, 99% of u infinity, just kind of eyeballing some locations here. We tend to again see that u infinity, that velocity is 99% of u infinity further away from the plate. So this is probably the a crude approximation of the boundary layers in both cases. If we look at the case with the higher speed, what we see is outside of the boundary layer, the fluid flows without deforming. Right in the boundary layer, we see a large deformation, lots of shear stress acting on the fluid, causing it to deform into that parallelogram. Again, at the very bottom of it, the velocity profile is equal to 0, the no-slip condition, tremendous amounts of shear at the surface of the plate. And again, right on the boundary layer itself, we see translation and just a very small amount of deformation of the fluid. So here, let's examine the effect of the Reynolds number on the thickness of the boundary layer. And we're going to define the Reynolds number. We'll use the subscript L to represent the length scale in this case. So in our case, both plates, or both scenarios, this value of L is equal to 0.5 meters, and that's true for the case on the top and the case on the bottom. The question is, does increasing the Reynolds number have any effect on the thickness of the boundary layer? And if it does it increase it or does it decrease it? Well, let's compare. We can look at a value of x of around 0.25, something like that. We can examine the thickness of the boundary layer at that location. Similarly, we can examine the thickness of the boundary layer at this location. Well, it's evident that the slower velocity profile tends to have a thicker boundary layer within that region. So the thickness of the boundary layer there is thicker than the boundary layer on the bottom. And the Reynolds number on the bottom is 5 times larger than the Reynolds number on the top. So indeed, increasing the Reynolds number will decrease the thickness of the boundary layer.